Okay, think about this. You've got high-performance race cars and modern airliners. They are, without a doubt, two of the most advanced machines humans have ever built. So you'd think they'd be sharing all their best tech, right? Well, it turns out they're separated by this huge engineering divide that's hiding in plain sight. Let's dig in. So let's start with a little puzzle. What's a piece of critical sensing tech that a Formula One car depends on for every single fraction of a second that a multi-million-dollar 787 Dreamliner just doesn't have? The answer is actually pretty simple, and man, does it reveal a massive difference in how these incredible machines are designed. The whole secret, the whole key to this, is all about how these two machines measure invisible forces. We're talking about the pushes and pulls on their suspension and their landing gear. It really comes down to understanding what the vehicle is feeling, moment by moment in real time. Look, if you want to squeeze every last drop of performance out of a car, or design a system that can take a ridiculous amount of punishment, you just can't guess. You have to measure it. Engineers have to know exactly how forces are moving through the suspension. Sideways in a corner, up and down over a bump, forward under braking, everything. And let me tell you, in the car world, especially in the super high-stakes world of motorsports, they have become absolute masters at this. They've developed some truly mind-blowing tech to literally see these invisible forces. At the heart of it all is this thing, the strain gauge load cell. Now, it sounds super complicated, but the idea behind it is just brilliant. You take this hypersensitive resistor and you bond it to a piece of metal. When that metal stretches or bends even a microscopic amount, the electrical signal from that resistor changes. And by arranging them in a special circuit called a Wheatstone bridge, you can measure those tiny, tiny changes with just astonishing precision. And when I say precise, I really mean it. This number, nonlinearity, is basically how much the sensor's reading strays from a perfectly straight line. At just 0.02%, it's almost perfect. What that means is, if you double the force, the sensor gives you exactly double the reading. No fuzz, no guesswork, just pure data. And it's the same story with repeatability. It means if you're on a track and you hit the exact same bump 100 times, you get the exact same force reading 100 times. That kind of consistency is everything. It's what lets engineers trust the data 100% so they can make these tiny little adjustments that, add up to winning the race. So what are we even talking about force-wise? Well, during some aggressive testing or a race, a single corner of the car can feel vertical forces that are 1.5 to 3 times its normal weight when it's just sitting there. That happens when it slams into the bump stops. And these sensors have to measure those massive spikes just as accurately as they measure the tiny little jitters. And this is where it all comes together in what's called K&C testing. That's for kinematics and compliance. They put a car on this massive rig with more than 70 sensors, measuring every single force, every movement, every angle. What they get is basically a complete 3D map of exactly how the suspension behaves under any condition imaginable. It is the absolute gold standard for understanding a car. Okay, so we've got this tech. It's incredibly precise, it's super reliable, and it gives engineers this perfect picture of what's going on with the car, which, of course, leads us to the really big question, right? Why wouldn't you want this level of crazy detailed, real-time data on the landing gear of a passenger jet, a machine that costs hundreds of millions of dollars and carries hundreds of people? Why in the world doesn't it use this same system? Well, the answer has absolutely nothing to do with whether they can do it. It has everything to do with a deep, fundamental philosophical difference in how you manage risk when failure is simply not an option. And this, right here, is where the two worlds just completely split apart. In the automotive world, we use what's called condition-based monitoring. Simple. Your brake pads look worn out, you replace them. But in aviation, for really critical parts like the landing gear, they use safe life design. And that philosophy is dead simple. You replace a part after a set number of flights or hours, period. It doesn't matter if it looks brand new, its time is up. Safe life is an extremely conservative way to do engineering. You basically test a component until it breaks, you figure out its fatigue limits, and then you say, okay, this part must be retired from service way, way before it could ever possibly get close to that limit. You don't wait for a sensor to tell you something's getting worn out. You just replace it based on a preset, unchangeable schedule. So why take this approach for landing gear? Well, for one, unlike, say, a wing, it's not designed to be damage tolerant. It uses these ultra-high-strength materials where a fatal crack could be microscopic, way too small for anyone to reliably find during a field inspection. And to even get certified, the gear has to prove it can handle 1.5 times the biggest load it will ever see in real life. The safety margins are just baked in from day one. This table really just lays it all out, doesn't it? A car deals with pretty continuous, mostly predictable loads from a road. A plane's landing gear has to deal with the violent, sudden shock of landing. We're talking sync rates of 10 feet per second. Plus, these insane spin-up and braking forces. The car is all about real-time optimization. The plane is all about absolute, non-negotiable safety margins. And the consequence of failure? Well, a car breaks down. A plane? It's catastrophic. It's a whole different ballgame. But this doesn't mean the aviation world is just, stuck in the past. They aren't ignoring how great sensing tech can be. They're just coming at it from a different angle, developing a solution from the ground up that can meet their insane requirements for safety and durability. The reality is, just slapping traditional strain gauges onto landing gear and making them tough enough to last for decades of flights through all kinds of weather, it's just incredibly hard. So the industry is actually leapfrogging that tech and working on something way more advanced. The future is all about stuff like fiber Bragg grating sensors. These things use light shooting through fiber optics to measure strain. That means they're totally immune to electrical interference and are way, way more durable. The big goal here is to use them to monitor for things like hard landings, and then use predictive machine learning to get a much smarter estimate of a part's remaining useful life. And this isn't just some science fiction idea. The big players, like Airbus, are deep into this research right now. They have projects like ALGSMO, which stands for Advanced Landing Gear Sensing and Monitoring, that are creating these exact kinds of cutting-edge, optically based systems. So this is the future. You combine the absolute safety of that old-school safe life philosophy with smart, next-generation data. So at the end of the day, the reason a 787 doesn't have the same sensors as an F1 car isn't because one is better than the other. It's because they are solving fundamentally different problems where the consequences are worlds apart. It really makes you wonder, doesn't it? What's another piece of technology that you just assume is everywhere, but is actually held back by a completely different way of thinking? Something to chew on.